to check here, but there are some more factors are here, are there. The first one is the number of turns of the coil. See, for that one, I made this arrangement. Here I made a big coil with different number of turns. So first I winded 500 turns and took a loop and connected to this connector. After that I continued winding, and after completing the 1000 turns, I made the connection here like that. For 1500 turns, for 2000 turns, and for 2500 turns, I made different number of turns. So using this one, I can conduct experiment on what is the effect of the increase in number of turns. So for that I am going to use these neodymium magnets as to produce the change in magnetic field, and to see the effect or to measure the induced EMF, I am going to use this LED. See, I connected the LED at the connector of 500 turns. You can see the brightness of the LED when I introduce these magnets to inside the coil. See the brightness. So after that I am going to connect it to 1000 turns. You can see the brightness is increased little more. So after that I am going to connect it to 1500 turns. You can see the brightness is still more increased. Like this, if I go on checking by increasing the number of turns, the induced EMF also increase. That I detected it using this LED brightness. In the same way, so I am going to check it in another way also, madam, using the digital voltmeter module. So I am going to connect the digital voltmeter module to 500 turns. Now see, there is no EMF induced because there is no change of magnetic field here. So now I am going to introduce these magnets into the coil at 500 turns. You can see the reading, how much voltage it is getting. That means how much we can say it as induced EMF in the form of voltage. See madam, you are getting 0.41 volts per 500 turns. After that you can see, sir, I am going to connect it for 1000 turns. You will get increased EMF. See here, 0.80, that means this doubles. The 500 turns to 1000 turns, 0.40 volts increases to 0.80 volts. That means whenever there is an increase in the number of turns in the coil, there is an increase in the induced EMF. So this is one part. The second part is that means the second factor influencing the induced EMF is strength of the magnetic field. See here I use some 5 magnets. If I increase the number of magnets and I insert it into the coil, the induced EMF also increases. If I decrease the number of magnets, induced EMF also decreases. In the same way, if I increase the speed, that is rate of change of magnetic flux increases, the induced EMF also increases. That you can see here. See there, you are getting 1 point something, 1.5, 1.92, 1.17 like that. That means if number of the rate of change of magnetic flux increases, induced EMF also increases. In the same way, the copper wire I taken here is a 35 gauge copper wire. If I increase the gauge, that means if I reduce the area of cross section of the wire, induced EMF also increases. In the same way, if I increase the area of the coil, total area of the coil, there also there is change, like if the induced EMF increases. So this is the second part of the experiment made by Michael Faraday. Then after this, on the basis of these two, dynamo is invented. So this is the simple dynamo that I made on the basis of this Michael Faraday's electromagnetic induction. So this is the stator and this is the rotor. Stator means this is the coil which is not movable. Rotor means it can be rotated. So for rotor I used neodymium magnets. So in this way, here for rotating this magnets, I am going to use the mechanical energy. So here mechanical energy is converted into electrical energy on the basis of Michael Faraday's electromagnetic induction. So this principle is used in our daily life in the production of electrical energy in generators, dynamos, and also in motors. Also the same electromagnetic induction can be used, and even in the transformers. Let us see how a transformer works on the basis of this. For this setup, I am going to use this as the primary coil, and a soft iron rod I am going to use, madam, and cells. For secondary coil, so which is of low turns. Here it is having only 500 turns, and this coil is having total of 2500 turns. So I am going to insert both the coils at one place, and I am going to give it a DC power supply and a switch is been adapted for this. For that one I made arrangement here. So this is the item prepared for getting DC current as well as AC current. First I will use this DC current to perform this experiment. So I am going to connect a connector from DC power source to the device here, and I am going to operate the switch here. So when I press the switch, you can see some flickering in the LED, and when I switch off and switch on, in both the times you can notice the flickering.
Now
you can see here the switch is off.
band.
You can see here, sir and madam. So this is the primary coil. Whenever there is a change in current in the primary coil, it creates a changing magnetic field. That change in magnetic field induces an EMF in the secondary coil or coil 2. So that you can see whenever I switch on and switch off the power supply here. So whenever I switch on and switch off, you can see the flickering. That is, an EMF is induced in the secondary coil. The same experiment I am going to perform using AC current. So for that I am using here a 12 volt AC supply here, and I switch on switch the power supply on, and you can see from top across the soft iron rod I am inserting the secondary coil. You can see there is a continuous glow of LED. That means here the current is changing continuously at the rate of 50 cycles per second, because I am using here the AC current. That is the property of AC current. That is why it is continuously blinking. So in the last experiment it was not continuously blinking, because I have to switch on and switch off to change the current. But here there is no need to switch on and switch off. It is automatically switching on and switching off. So like this, and if the distance between these two coils is decreased, the induced EMF increases. You can see it here now. So this is called as the mutual induction, and this principle is applied in step down transformers and step up transformers. And this totally what I can say, the application of Michael Faraday's electromagnetic induction is seen in dynamos, motors and transformers. Thank you, madam. This is my presentation, and you can go for the next procedure, madam.